We're going to start our discussion of section 3.4 by reviewing a few things you should have learned while doing your reading homework.
Some things we've already learned about. Instantaneous velocity can be represented by the slope of a tangent line on a graph, while average velocity would be the slope of the secant line. Instantaneous velocity can be calculated using the derivative. Position, velocity, and acceleration are all related because velocity is the rate of change of position and acceleration is the rate of change of velocity. In other words, velocity is the derivative of position and acceleration is the second derivative of position. Speed and velocity are both words that sometimes are used to talk about the same thing, but they really are different. Speed is a scalar, meaning it's only related to the number that describes how fast an object is moving. Velocity is a vector. It's referencing both the speed at which something is traveling, but also includes the direction in which it is traveling. Let's go ahead and work through the examples you were asked to take a look at. So part A here says to find the velocity function, which would be the first derivative of the position function you were given. We can use the power rule to find this and get 3t squared minus 12t plus 9. Part B asks us to find the velocity after 2 seconds and 4 seconds. So we substitute 2 into the previous expression. Evaluate that and get -3. Don't forget to include units here, which would be meters per second. We do the same thing with 4, and we get 9 meters per second. Part C is asking us when the particle is at rest. At rest means that it is not moving, which means that the velocity is equal to 0. So we take 3t squared minus 12t plus 9 equal to 0. Solve that quadratic equation whichever way we feel is most appropriate. I like to factor. I see that there is a common factor of 3 there, so I will factor it out. I could also divide both sides by 3. Doing so here, dividing both sides by 3, I get 0 equals t squared minus 4t plus 3. And if I factor that remaining expression, I get t minus 1, t minus 3. Set those each equal to 0, and I get t equals 1 or t equals 3. Don't forget units. Time is measured in seconds here. Now for part D, we want to figure out when the particle is moving forward. Remember that velocity, unlike speed, includes direction. So if we are moving forward, that means we want the velocity to be positive. Now it might be tempting to take our previously factored expression and set each factor greater than 0. But that would be wrong. We cannot do that because when we are multiplying something, if each of those factors was negative, that would also give us a positive result. So anytime we're dealing with factoring and solving inequalities, we need to solve this by checking each interval that is split up by the solutions we got in part C, the places where that expression would be equal to 0. Check the intervals between those values. So we'll do that now. I like to think of this as a number line. There are different ways you could show your work here. So I'm checking velocity, 1 second and 3 seconds. For time, I know that the velocity is equal to 0. In between each of those, I would pick a t-value to test in our velocity function. For example, less than 1, I could pick t equals 0, substitute that into our velocity function, which we found earlier in part A, And if I substitute the 0 into this expression here, I get 9, which is a positive number. So coming back to part D, I can say, well, velocity is positive on that interval. In between 1 and 3, I can pick a value for t in between there. Let's say I choose t equals 2. Remember, I could pick any value. So I could pick 1.1 or 2.7843, anything I want in between 1 and 3. But I'll pick 2. It's a nice, easy value. And we've actually already computed it earlier and got -3, so we know that velocity is negative on that interval. So we will not be including that as part of my answer, because over that interval from 1 to 3 seconds, we're moving backwards since velocity is negative. Now we check our final interval when t is greater than 3. So I can pick a number like 4 or 5 or 1,000,000, because that's greater than 3. And again, we can use some of the work we've already done. Back in part B, we computed v of 4 and got 9. So we know over that interval we are going to get positive velocities. So coming back to answer the question here, when is our particle moving forward? We're looking for positive velocities. So that would be these two intervals when we are less than 1 or greater than 3. So I could write that out in interval notation like this. But that doesn't really get to the point of time being measured in seconds, so I could also write t less than 1 second and t greater than 3 seconds. So pay attention to directions. If it asks specifically for interval notation, give your answer the first way. But a lot of times it's nice to remind us what the units are for these, so it's also nice to write it the second way, or you could write it out in complete sentences. One other thing to point out here as well, remember we are measuring time in seconds, and we usually don't consider negative time. Now our original statement of the problem does not tell us to ensure that t is greater than 0, so in this case we're all right with the way we wrote our answer. But a lot of these problems will add a statement that t has to be greater than 0. So keep that in mind. If this statement was included, I would need to make sure that my interval had a 0 here rather than a negative infinity. So always read the problem statement very closely. All right, part E asks us to draw a diagram. It does not ask us to graph the velocity function. That's not what we're asked to do here. We'll be asked to do that later, but for now we're just drawing a diagram to represent the motion of a particle. So think of this as a picture you would draw, really just tracing the motion of that particle. So if I'm this particle, when t equals 0, I am moving forwards. We know that because in the previous problem, we checked the intervals over which my particle is moving forwards and backwards. As soon as I hit t equals 1 second, I stop and then turn around and start moving backwards until I reach t equals 3 seconds. I stop again, and then I turn around and start moving forwards again and do so indefinitely. If I had wanted to here, I could have even continued this, since again, we did not emphasize that we were starting this at t equals 0, but that is usually the case for these. So I didn't necessarily need to include that portion over there. So this is one way in which you could draw a diagram. There's a few other ways, but I really want to emphasize that a diagram is not the same as the graph of the velocity function. Moving on to the second page, we're asked to find the acceleration. So the acceleration function is the derivative of velocity. It's the rate of change of velocity, which, as a reminder, is the second derivative of the position. And I've written the velocity function there as a reminder. So again, just taking the power rule here, we get 6t minus 12. And to find the acceleration after 4 seconds for part G, we just substitute 4 into that expression we just found, and we get 24 minus 12 is 12.
Meters per second squared. Don't forget those units.
Now to discuss parts H and I, we're going to go ahead and switch over and use Desmos to help us out here. We are now asked to use the graph to help us figure out when our particle is speeding up and when it is slowing down. This is different than what we looked at earlier regarding moving forwards and moving backwards. But it is similar in that we do still need to look at where things are positive and where they are negative. So we have our three graphs here from 0 to 5. And really, we don't need the position graph here. So I don't need to use the red initial position graph. I'm really just focusing on velocity and acceleration. And I want to give you an example to help you understand why. Imagine you are in a car. It's not moving. Let's say it has an automatic transmission to make things a little easier. So the car is currently in park. If you want to move forward, you would put the car in drive. And that would cause the car to slowly start moving forwards. If you want to move faster, or in other words, speed up, you would hit the accelerator pedal. So putting the car into drive causes you to have a positive velocity because now you are moving forwards. But if you want to speed up, you need to apply acceleration in that forwards direction. So in order to speed up, you need both velocity and acceleration to be positive. Now you could always speed up in the opposite direction as well. Imagine you put your car in reverse instead of putting it in drive. Your car would then have a negative velocity because it is moving backwards. And if you wanted to move backwards even faster, you would again hit the accelerator pedal, which would cause you to accelerate, but now in the negative direction. And you would be moving faster. You'd be speeding up just in the backwards direction. So not only is it that both velocity and acceleration have to be positive, they could also both be negative, meaning that you're moving backwards and moving faster in that backwards direction. So it's really that both velocity and acceleration have to have the same sign, both positive or both negative. And we can use the graphs to help us find where that happens. Remember, we're only looking at velocity and acceleration here. So if I look for, let's start where they're both positive. So where is acceleration positive? Here, but velocity is only positive from 3 onwards. So they match there. Is there anywhere else they are both positive? No. But is there anywhere that they are both negative? Well, it looks like velocity is negative from 1 to 3, but acceleration is only negative when we're less than 2. So where do those both match? Well, that would be from 1 to 2. So I can say that we are speeding up over the intervals from 1 to 2 and from 3 onwards. Now we want to look at where we're slowing down. So in our example of driving a car, this would be if we were to apply the brake pedal rather than the gas pedal. So if I am already traveling forwards and I want to slow down, I hit the brake pedal, applying a deceleration to my forward velocity. So velocity would be positive, but acceleration would be negative. And we can see that happening from 0 to 1. My velocity is positive, and my acceleration, although it's off the screen, I can see it's continuing in that negative values. So from the interval 0 to 1 here, we are slowing down. Is there anywhere else this happens? Yes, there is. We have a negative velocity from 2 to 3 seconds, so the car would be traveling in reverse, but my acceleration is now positive. So when I'm hitting the brakes, the acceleration is in the opposite direction as the velocity, and that would slow the car down. So we are also slowing down from 2 to 3 seconds here. Moving on, we're going to take a look at our business example. So we have a cost function here, and we want to know the cost of producing 500 items. So we're simply substituting 500 into that cost function, grabbing a calculator, and evaluating. And that gives us $15,000. Don't forget your units. Now, marginal cost, remember, is the rate of change. So that will be our first derivative of the cost function, which is just 5 plus 0.02x. And the marginal cost of producing 500 items, well, that's, again, just using part B for that rate of change. So substitute 500, and we should get 15. Don't forget units. It's a rate of change. So cost was measured in dollars, and our variable x was measuring the number of items. So it's $15 per item. Now part D is asking us to compute the actual change of cost from the 500th item to the 501st item. So we need to calculate C of 500 and 1 minus C of 500. So we have 15,000, 15 and 1 minus, sorry, that should have been a decimal. C of 500 was 15,000 even, and we get 15.01. So we're asked to compare that to our answer in part C, because what we just computed is the actual cost of producing that 501st item. If I go from having 500 items and then 501 items, and I just calculated that I spent an extra $15.01, why is that not the same as my answer in part C of my rate of change? Those should be the same. That's the point of using the derivative, so that we don't have to do this calculation every single time. Well, the problem here, and the reason why we're getting slightly different answers, why we're off by a penny, is because in reality, a cost function can't be continuous. We can't produce 500.1 item, 500.2 item. We go straight from 500 to 501 to 502. If I was to graph this function, it would not be a nice smooth curve. It would be a series of points from one item to the next. So it's not actually continuous. We're estimating it as a continuous function so we can do a lot of this calculus work. But in reality, we're going to be a tiny bit off because we don't have a continuous function. Now, for you future biologists in the class, we didn't go over any of the population growth problems, but for those problems, we would run into a similar issue. If you're considering the population, you would go from 1 person to 2 people to 3 people to 4 people. We would not go from 1 person to 1.1 to 1.2. You can't have half a person or a third of a person. So you would run into this same problem. This is the difference between a discrete function of individual items versus a nice continuous function.